Welcome to another module in this massive open online course. So we are looking at channel coding, and in this module we start looking at a different class of channel codes termed as convolutional codes. Okay, so we want to look at convolutional codes, which are basically a class of channel codes. And we have seen a channel code is basically nothing but a paradigm which introduces systematic redundancy to recover from errors introduced by the channel. This is a class of channel codes, or which are also known as error control codes. Or error control codes. Okay. Now, consider an information bit sequence. Consider a bit sequence. Okay, and this can be possibly infinite. Possibly infinite. Okay. Now, an example of a convolutional code can be defined as follows. Example of a convolutional code is given as follows. We have C0 J, this is equal to xj plus xj minus 2. So this is code bit 0. So xj's are obviously the information bits at time instant j, time instant j minus 2. This is the code bit 0, at time j, code bit 1 at time j equals xj minus 1 plus xj minus 2, and this is your code bit 1. Code bit 1 at time j. Okay. Now, what is the meaning of this? So, remember, there is for at each time instance we are generating, that is for each information bit we are generating. So, at each time instance, first observe at each time instance, that is at each time instance for a single information bit xj, or at each time instant or for each information bit for each time instant, two code bits are generated. C0j implies, now obviously I am getting at the rate. Remember, the rate is number of information bits divided by number of code bits. This is equal to half, because for every information bit you are generating two code bits. So this simple code has rate equal to half. This is a rate half code. For every information bit you are generating two code bits. Okay, so redundancy is half. Remember, we said as the redundancy increases, the rate decreases. So this has a redundancy of half. Okay. Now, further, this addition, if you look at this addition, this is an important point. This is addition on the binary field. This is something new This is known as binary field arithmetic. Binary field arithmetic means that is, if you look at binary field arithmetic is basically, in addition, is basically 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0, and this is a bitwise operation. 1 plus 0 equal to 1, 1 plus 1 equal to 0. This is an XOR. So, you can see this is similar to an XOR. Addition over the binary field is similar to an XOR operation, and multiplication, 0 into 0 equals 1 into 0 equals 0 into 1 equals 0, 1 into 1 equals 1. So, this is similar to an AND operation. Okay. So, this is basically your binary field arithmetic. Okay. This is a bitwise operation, binary field addition, which is similar to the XOR operation, and multiplication, which is similar to the AND operation. And you can see this satisfies several properties. We will not go into the details of that, but you can see the properties, several properties are satisfied by this plus and dot operations. If you look at these properties, we have commutativity, these are termed as commutative, that is, it commutes, that is, a plus b equals b plus a dot b equals b dot a. Then it's associative, both the operations are associative, that is, a plus b plus c equals b plus c or equals a plus b plus c. A dot b dot c equals a dot b dot c. Further, distributive, you can see that these operations are also distributive. A dot b plus c equals a dot b plus a dot c and so on, or a plus b dot c equals a dot c plus b dot c and so on. Okay. Now, so this is the binary field arithmetic, which we are going to use exhaustively. That is, as we deal with convolutional codes, we are going to use this binary field arithmetic exhaustively. Alright, so it's important to familiarize yourself with this binary field arithmetic. That is, addition is the XOR operation, XOR operation, and multiplication is the AND. And they obey this series of properties, which is commutativity. That is, the order is not important. That is, a plus b is b plus a dot b is b dot a, associativity, and also the distributive property. Okay. Now, one thing which is important is we want to see is this code, we want to ask the question, is this code a linear code? For instance, let us consider two information bit sequences. Consider two information bit sequences, x0, x1 up to x0, x1, x2, so on. Okay. This is the first information bit sequence. Another information bit sequence is y0, y1, y2. Okay. So, these are the two information bit sequences. Now, the code bit 0 due to xj code bit 0 at time j due to information bit sequence x is xj plus xj minus 2. This is the coded bit corresponding to for sequence x. Similarly, the coded bit y, coded bit 0 for sequence y will be yj plus yj minus 2. Now, if you look at, so this is the coded bit for coded bit 0 coded bit 0 for sequence y. Now, you can see what happens when you add these two coded bits C0 of x, C0 of y of j, that will be xj plus xj minus 2 plus, well, yj plus yj minus 2, which is equal to, using commutativity and associativity, you can prove that xj plus yj plus xj minus 2 plus yj minus 2 which is, this is arising from commutativity and associativity. And now if you see, this is nothing but corresponds to the coded bit generated by the addition of the information bit sequences x and y. So, this is nothing but the coded bit 0, correct. If you add the information bit sequences x and y, what you will have is x, the jth bit will be xj plus yj, the j minus 2th bit will be xj minus 2 plus yj. So, this corresponds to the coded bit generated by the addition. So, by adding the code sequences, right. So, there are two different things. One is you are adding the code sequences corresponding to the two different information bit sequences. The other is the coded sequence generated by the addition of the bit sequences. So, you can generate the code sequences and add them, or you can add the bit sequences and generate the code. Both these things are similar. This implies that this code is a linear code. That is the important point. So, here this is the coded bit for additive, added, information bit sequence. So, what we have is this important property C0x C0y is equal to C0 x plus y. That is, what we have is basically code followed by addition, and this is basically addition of the information bits followed by code. This is and both are equal, which implies that code is, which implies that the code is linear. Okay, so that's an important property which one can keep in mind, that this code, we have looked at a convolutional code. Now similarly, this property can also be shown for coded bit 1. Alright, we have only shown it for 0, you can very easily show it. In fact, it's almost trivial that C1x plus C1y of j equals C1 of x plus y of j. So this is coded bit 1. Okay, so this is for bit 0. Remember, there are two code bits. One is code bit 0 or coded bit 0 or code bit, not coded bit 0, code bit 0. Okay, so that's what we have shown. So we have introduced a convolutional code, which we have said is basically convolutional code. An example of a convolutional code, of course, this is not the only convolutional code, but this is one particular example of a convolutional code. Again, convolutional codes are basically belong to there is basically a class of error control codes or a class of channel codes, which can be used to recover from the errors, recover from the errors, or basically reconstruct, correct the errors, right, arising over the channel, correct the errors arising over the channel. Okay, and we will explore the properties of this convolutional code, the generation, the encoding and the decoding aspects of these convolutional codes in subsequent modules. Thank you very much.